So what I want to do in this video is do another related rates problem. In the previous video we did related rates and we figured out how fast the height of a ladder is increasing depending on how fast it's getting closer to the wall. So if you haven't watched that one, watch that one first and then come to this one. Alright, so this problem is actually from tutor.lamar.edu, so shout out to him. Let's get started. Air is being pumped into a spherical balloon at a rate of 5 centimeters to the third a minute. So let's sort of draw out what's going on. So we have some sort of sphere, and it's a balloon. The balloon has some hole that air is coming in from, and this hole is allowing air to come in, which increases the volume of the balloon. We know its volume because it's centimeters cubed at 5 centimeters cubed per minute. So let's call this V prime, right? This is how fast how fast the volume is changing, right? So the change in volume, or the derivative of volume. All right, let's see what it's asking. Determine at the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. Okay, so this is important because we have to notice that the radius increase is not constant. It's proportional to the volume increase, but you can even think about it intuitively. When you start pumping a balloon, first it pumps really fast, right? And the radius increases quickly from 0 to something. And then towards the end, you're still increasing the volume by the same amount, but then the balloon seems like it's not getting as bigger faster, right? The increase in radius starts to slow down. So that's why we're looking for the rate of increase at a certain diameter of the balloon. So we were trying to find r prime. So we're trying to find r prime. I'm going to write a question mark. That's what we're trying to find. When the diameter is 20, so when the radius is 10, right? So when the radius is 10 centimeters. All right, so let's see how we can do this. Well, we're going to use related rates. We're going to relate rates here, and relate derivatives here, to figure out what we need to figure out. Well, first of all, let's define the volume of a sphere. Volume of a sphere is 4/3 pi r squared, pi r to the third, right? Because we need the units to be to the third power, it's volume. So let's take the time derivative of both sides, and let's see what happens when we do that. Well, the time derivative of the left is just v prime, right, or dv dt. And the right side, well, we have 4/3 pi, the derivative of r to the third, this is just constant, so that stays there, right? And then the derivative of r to the third, well, that's 3r squared r prime, right? Because the chain rule, we have r is in terms of time, so we multiply that by r prime. So let's simplify this a little bit. We notice that the 3's cancel, so we're left with v prime is equal to 4 pi r squared r prime. Now let's think about what we're solving for here. We're solving for r prime, and here we have many variables. We have v prime, and we have r, and then we have r prime. So that's, we have one equation, 3 variables. That's not too good. However, we have the values of the other 2 variables that are in this equation. So we can actually get r prime alone, plug in the values we have for v prime and r squared, and we're actually done. So let's get r prime alone. Well, r prime alone would be v prime divided by 4 pi r squared, and we know that because we just divided by 4 pi r squared on both sides. And we know the value of v prime, that's 5. We know the value of r squared, again, it's at when r is 10, so r squared is 100, and then times 4 pi, so we get r prime is equal to 5 over 4, I'll just say 400 pi. Then you can plug this into your calculator. Here, let's estimate it. Let's think of what the estimate would be. 4 times pi, that's around 1,000, maybe 300 or so, right? And then 5 divided by 1,300 or so. Let's see. 5 over 13, we can estimate to be around a bit less than 0.5, so we'll just say like 0.4. And then there's a factor of 100 on the bottom, so we divide 0.4 by 100, right? So it's 0.004, I believe, 0.004. So around there, right? This is not exact, but you can just plug this into your calculator to get a more exact answer. But the rate of increase of the radius at r equals 10 centimeters, given the pumping air is 5 centimeters to the third over a minute, is 5 over 400 pi centimeters per minute.